this is a design example 4.4 from course text. The objective is to design the bias of the MOSFET circuit such that the Q point is in the middle of the saturation region. Now, if you recall in the part 40 of the this video lectures on MOSFETs, uh, we were given the values of R1, R2, and RD, right? And the values that we obtained for ID and VDSQ were arbitrary. Okay, now you cannot have the arbitrary values of VDSQ and ID for given R1, R2, and RD resistances. The reason is, now if you consider the load line over here, if this Q point is near non-sat region, or it is biased towards the cutoff region, your output swing is going to be limited. Okay, it can be chopped off. For example, if it is the crest could be chopped off if it is around the cutoff. Okay, you might not have the maximum amplitude. Similarly, the lower region of the input or the amplified sinusoid can be cut off if it is near the non-sat region. So preferably the Q point should be somewhere in the middle of the load line. Okay. Now, to ensure this problem requires the design as such that you have to find the values of R1 and R2, which make sure that the drain current and the VDSQ, the Q point. So the Q point consists of the VDSQ and the drain current. This point, which intersects the IV characteristics of the transistor, these are the black lines are the IV characteristics of the transistors. In saturation region, the intersection of the load line with the IV curve should be as such that this point lies in the middle of non-sat region. This is the non-sat transition point and the cutoff point. Okay, so in between these 2 points, we are supposed to have the Q point. So let's try to find out these biasing resistors which can guarantee the Q point to lie in the middle of the load line between the middle of the non-sat and cutoff regions. Okay, so the circuit to be designed has the configuration shown in figure 17, and you can see that this is the common source NMOS transistor circuit because the source terminal is common, it's ground. Okay, so let R1 and R2, the parallel combination is given. Okay, so as a design constraint, your parallel combination of R1 and R2 biasing resistances is given as 100 kilos. It has to be 100 K. So design the circuit such that the Q point IDQ is 2 milliamps and the Q point is in the middle of the saturation region to have the maximum swing, output swing. The choices are that you have a transistor available with the nominal parameters of threshold voltage as 1 volt. The conductivity parameter is given as 80 microamp per volt squares. Width to length, channel width to length, geometrical parameters is given. The ratio is about 25. And the channel modulation parameters in volts inverse is given as 0.015. Okay, so this transistor is available and the given attributes of the parameters are there. Now, from this information, the first thing you want to do is we find the conduction parameter as W by L Kn by 2. Okay, so W by L is given as 25. Okay, this electrical conduction parameter is 80 microamps per volt square. So in milliamp per volt square, you find this as 1 milliamp per volt square. That's your conduction parameter Kn. Okay. Now let's get back to the problem. How we ensure that the Q point is at the center. So what are the values of R1 and R2? So the DC, it has to design. It has to start with the DC design. Okay. The Q point is finding the Q point is the DC analysis. Okay. So the load line and the desired Q point are given in figure 18. This is figure 18, which shows the DC load line, the transition point for NMOS, and the transition point for the NMOS circuit in figure 17. Okay, so for this circuit of figure 17, you have the IV characteristics, and you have the transition point over here. This is the transition point given as VDS sat, VGS minus VTN. This is the transition point. So we first to calculate VDS sat. That is the transition point between non-sat. This is the non-sat region. So this is your non-sat on the left, and then you have the sat region on the right. Okay, you can see that the current is independent of VDS. All right, so it's an ideal MOSFET characteristics shown over here. So at the transition point, the subscript T indicates the transition point values. How do you determine is that, okay, now in the question, the quiescent current or the quiescent drain current, that the drain current was supposed to be, the outcome of the design should be as such that these resistances, these biasing resistances, the gate source voltage should be as such that the drain current should be 2 milliamps, okay, and it is supposed to be in the saturation region. So we use this saturation voltage, gate source voltage and current relationship, and to find the transition point, since this is supposed to be 2 milliamps, and this has to be halfway between the cutoff, so the cutoff is at 0, and the transition, since this has to be halfway, then that means your transition point where the transition occurs between the saturation and non-sat should be 4 milliamps. Okay, so since 2 milliamps is the halfway, so 4 milliamps is where you exit the saturation current and then you go into the non-sat region. So let's use the same relationship over here, and we have the conduction parameter that we found previously. That's 1 milliamps per volt square. That's the transistor cutoff, transistor conduction parameter. Threshold voltage is given as 1 volt. Okay, so let's plug those values over here. So we have 1 over here as the conduction parameter. 1 is the threshold voltage of the transistor, minimum voltage turn on the transistor, and where the transition occurs, ID is 4 milliamps. Okay, ID is 4 milliamps. So from there you solve the quadratic and you select VGST as 3 volts. The reason for finding out this VGST from the IV relationship of the saturation region of transistors is that from VGST you can find what is VDST, that is the drain to source voltage at saturation transition point, because if you find this point, then that means between this point and VDD, because VDD is the other extreme of the load line, and this is the point where the ID, the drain current, is supposed to be 0, and that should be equal to 12 volts, right? Because okay, VDD minus IDRD is your VDS, right? Minus IDRD is your VDS. If you apply the KVL at the output loop, so these are the parameters for the. So if you apply the KVL, I'm applying the KVL over here, right? So VDD minus IDRD is V naught. V naught is basically VDSQ. So if ID is 0, if this is supposed to be 0, then this happens when VDD is VDS. Okay, so there is no potential drop. The drain voltage and VDD are at the same potential. That means no current flows through the drain resistor. Okay, this happens at 12 volts when VDS is VDD, right? So so what I was saying is that if you have VGST, then you can have corresponding VDST. Okay, so if you have this point, then you have this point. It's easy to find what is VDSQ, which is in the middle of these 2 points. So how do you find this? Is that VDST is the saturation point, which is given as the overdrive voltage by definition. So VDST, VDS sat over here is given. Okay, so I don't need to write this. VDS sat is VGST minus VTN. Okay, so we have found what is VDST. That is 3 volts. 3 volts minus 1 volt is 2 volts. So this comes out to be 2 volts. Okay, and this point is 12 volts. So the difference is about 10 volts. Okay, so the halfway in between is 5 volts. So 2 plus 5 is 7 volts. So 7 volts is your VDSQ. Okay, VDSQ is supposed to be 7 volts. This is 7 volts, and ID is 2 milliamps. Okay, so you have 2 parameters from which we can find the biasing resistances R1 and R2, and then RD. Okay, as well. So this is where this is the point where you have the intersection of the DC load line and the IV characteristics just exactly in between the non-sat region and the cutoff region. Okay, so okay, now VDS2 is 2 volts, so the Q point is in the middle of the saturation region. Then VDSQ is 7 volts over here. You can see that. Okay, because this is 5 volts and then this is also 5 volts. So you can have a maximum swing of 10 volts peak to peak sine wave as the output. So which would yield a 10 volt peak to peak symmetrical output voltage without being clipped from either side. Then from figure 17, we can write, this is my figure 17, okay. So from here, if you write this, the same relationship that I have written before for the output KVL, if you apply the KVL at the output loop, now you have VDSQ, okay, so you have IDQ as well. So let's put it like this, VDD, I'm just rephrasing this equation over here. So VDD minus VDSQ divided by IDQ is going to give you the drain resistance, right? So I have IDQ as 2 milliamps, VDSQ is 7 volts, VDD is 12 volts, so everything is known. So I can have the drain resistor RD as about 2.5 kilo ohms over here, okay. Now my VDSQ is 7 volts, so I know what is ID, that is in the middle of, so ID and VDS are establishing the middle Q point, and this gives RD as 2.5 kilos, okay. So we can determine the required quiescent gate to source voltage from the current equation as follows. Now again, you use, since IDQ is the saturation current, you use the saturation VGS and IDQ relationship. VGSQ is to be found out. VTN is there 1 volts. Okay. Conduction parameter we have found out already as 1 volt. So this is equal to 2 milliamps. To solve the quadratic and find VGSQ, you find this as 2.41 volts. Okay. This is your VGSQ. And you can see that this is greater than VDN, so the transistor is on and it is biased in the saturation region. Okay, then how VGSQ is being established is through the biasing distances R1 and R2. Okay, I mean VGSQ is nothing but the voltage division which is established by R1 and R2. So we can write this as R2 over R1 plus R2, R1 plus R2. Multiply by VDD. Okay, multiply by VDD. Right. So the other thing is, we know what is the parallel combination of R1 and R2 is. That's 100K. Okay. So let's use this information as well. So 2.41 volts is VGSQ, which is being established by these resistors, which are unknown. But we know what is the what is R1 and R2. R1 parallel combination of R2 is supposed to be equal to 100 kilos. Okay, R1 and R2 is 100 kilos. So how we can use this relation? You can use this information over here. VDD is now, that's 12 volts. So let's multiply and divide this expression with R1. So this expression is same as R1 and R2. Just plug this 100 over here. Let's bring this 100. Okay, and then you have R1, which is the only unknown. VDD is 12 volts. Also remember that Ri is the input resistance of the MOSFET. So in the small signal model considered in the last lecture, this Ri input resistance looking into the MOSFET device, it's nothing but R1 and R2 parallel combination, because the gate capacitance is taken to be, the gate capacitive reactance is taken to be infinite. Okay, the input impedance of MOSFET is large, so it's just the parallel combination of R1 and R2. Okay. So let's plug this over 100 over here, and R1 is the only unknown, and VGSQ is 2.41 volts. So from here you find R1 as 498, and once you have R1 as 498, then from this relationship you find R2 as 125 kilo ohms. Okay. So we have all the resistances now. We have R1, we have R2, we have found RD. So we have all the three resistances which are ensuring the Q point to be equal to IDQ to be equal to 2 milliamps and VDSQ is 7 volts. So we are exactly in the middle of in the halfway between the non-sat and the cutoff regions. So this Q point is where the transistor is biased, and the resistors responsible for the biasing are R1, R2, and RD. Okay, R and R2 are biasing this. I mean, they are establishing VGS over here, so so that you can have a maximum swing when the Q point is at the center. Okay. All right. To determine the small signal parameters like transconductance, gain GM and the voltage gain. We use the same information as previously we did for the evaluation of the transfer difference gain. It's given as 2 square root of conduction parameter of the transistor and the DC Q current of the MOSFET into the drain terminal. That's given as that's found as since the IDQ was supposed to be 2 milliamps over here. Let's plug those values. Kn is 1. Then we find out that the transfer gain in milliamps per volt is 2.82. Small signal output resistance is given as 1 over lambda IDQ. Lambda is given as 0.015 volts inverse. Multiply by 2, that gives 33.3 kilo ohms. So let's plug those values over here. And from here you find for 0 output source resistance, we don't have any source resistance over here. So let's short circuit this over here, right? That means VGS is your VI. Okay, there's no loading. VGS is VI. So you can write this expression directly. So over here, this this is GM VI, GM VI into R naught parallel combination of RD with a negative sign due to the direction of the current as such. Okay, you should consider the direction of current is like this. The dependent current source and the current over here, they are opposite. So that means the VDS and your input voltage VI are just 180-degree phase apart. Okay, so the voltage gain is minus GM VI. VI can be taken on the left hand side over here into R naught RD, which is the output resistance. Okay, and that gives us to plug the values of R naught, that is the output resistance of the transistor. With this is RD. Okay, that's the drain resistance that we found out from here. This expression. Plug those values with the transfer reactance gain, you find the voltage gain is 6.58. Okay, and if you recall, this gain is a little higher than what we obtained last time, without making sure that the Q point is in between. So last time the voltage gain was 5.2, but the DC load line, on the DC load line, we didn't have the Q point in the middle. So over here, it's a little different. You have a higher voltage gain. Okay, although there is a phase reversal that's due to the common source configuration of the NMOS device, but we have a higher voltage gain. So that means you're going to have a symmetrical swing with a larger amplitude, okay, with a lot more peak-to-peak voltage. So establishing the Q point in the middle of the saturation region allows the maximum symmetrical swing, okay, in the output voltage. Thus, keeping the transistor biased in the saturation region allows the transistor to operate as a linear amplifier with the maximum output symmetrical swing. Okay.